Carbon makes up 0.02% of the Earth's crust and 0.03% of the atmosphere. Despite this, it's extremely important. Carbon forms the foundation of all living things and many synthetic materials. Look around you: food, clothes, medicines, and books all contain carbon-based compounds. Every living organism relies on carbon as its fundamental building block. Carbon's unique electronic configuration and bonding properties make it special. It can form strong bonds with itself and other elements, creating many molecular structures. This flexibility allows carbon to build complex molecules for life and serve as the basis for many modern materials. A covalent bond forms when two atoms share electron pairs. This sharing helps both atoms reach a noble gas configuration. Covalent bonds don't create charged particles, so the resulting compounds usually don't conduct electricity well. Carbon has 4 valence electrons and a valency of 4, making it tetravalent. It's hard for carbon to gain or lose these electrons due to the energy required. Covalent compounds have lower melting and boiling points and conduct electricity poorly. There are 3 types of covalent bonds: single, double, and triple, which involve sharing 1, 2, or 3 electron pairs respectively. Allotropes are different forms of the same element. They differ in how their atoms are arranged. Carbon has several important allotropes. Diamond is one, with carbon atoms bonded to 4 others, creating a rigid structure. This makes diamond the hardest substance on Earth. Graphite is another, with carbon atoms forming hexagonal layers bonding to 3 others, making it smooth and a good conductor. Fullerenes are a third category, with carbon atoms in spherical or ellipsoidal shells. Buckminster fullerene, or C60, is a famous example, named after architect Buckminster Fuller, with a spherical shape like a football. Carbon has 2 key properties that make it versatile. The first is catenation, where carbon atoms bond to other carbon atoms, forming chains, branches, or rings. These bonds are strong and stable and can be single, double, or triple. The second property is tetravalency, where each carbon atom forms 4 covalent bonds with other atoms. This allows carbon to connect with many elements, creating many combinations. Carbon's small size also helps form stable compounds, as it creates a strong attraction between the nucleus and electrons, holding bonds together firmly. These properties explain why carbon is the foundation of many compounds in living things and the world around us. Carbon compounds are classified in 2 main ways. They are divided into saturated and unsaturated compounds. Saturated compounds have only single bonds between carbon atoms and are called alkanes. Unsaturated compounds have double or triple bonds. Double bonds classify a compound as an alkene, and triple bonds classify it as an alkyne. Hydrocarbons, made of carbon and hydrogen, are classified into 3 categories: alkanes, alkenes, and alkynes. Alkanes have single bonds and the formula CnH2n+2. Alkenes have at least 1 double bond and the formula CnH2n. Alkanes have at least 1 triple bond and the formula CnH2n2. Saturated compounds have single bonds and unsaturated compounds have double or triple bonds. Alkanes have the most hydrogen atoms. Alkenes have 2 fewer, and alkynes have 4 fewer hydrogen atoms compared to their carbon count. Structural isomerism occurs when compounds have the same molecular formula but different structures. The atoms are connected in different orders, changing the molecule's appearance and behavior. Butane is an example, with the formula C4H10. It has 2 forms: N-butane, with a straight chain of 4 carbon atoms, and isobutane, with a branched structure. Both have 4 carbons and 10 hydrogens, but distinct properties due to their atomic arrangement. The physical shape and connections affect how the molecule interacts with other substances. Knowing the molecular formula is not enough. The actual arrangement of atoms is needed to predict a compound's behavior. Carbon compounds can be organized by their skeleton structure. There are straight-chain hydrocarbons, like procane, with carbon atoms linked in a line. Branched-chain hydrocarbons, such as isobutane, have a main chain with side branches. Cyclic hydrocarbons, like cyclohexane and benzene, have carbon atoms in closed rings. The saturated hydrocarbon series, alkanes, has a naming pattern based on carbon atoms. One carbon is methane, CH4. Two carbons are ethane, C2H6. Three carbons are propane, C3H8. Four carbons are butane, C4H10. Five carbons are pentane, C5H12. Six carbons are hexane, C6H14. Each additional carbon adds two hydrogen atoms, keeping the compound saturated. A functional group is a specific atom or group of atoms attached to a carbon chain. It determines how a compound behaves chemically. This property stays consistent regardless of the carbon chain's length. Common functional groups include haloalkanes with chlorine or bromine, alcohols with a hydroxyl group, and aldehydes and ketones with two oxygen atoms. Carboxylic acids have two oxygen atoms as well in the form of COOP. Heteroatoms are elements other than carbon and hydrogen in organic compounds. Functional groups attach to carbon chains, replacing hydrogen atoms, and give compounds specific chemical properties. A homologous series is a group of organic compounds with the same functional group. Each member has a carbon chain with a consistent pattern. The formula of each compound differs by 1 CH2 unit. Molecular mass increases by 14 units between each member. Physical properties, like melting and boiling points, increase as molecular mass gets larger. Chemical properties stay similar due to the functional group. There are three important series: alkenes, alkenes, and alkynes. Alkenes have single bonds and follow the formula CnH2n plus 2. Alkenes have double bonds and follow CnH2n. Alkenes have triple bonds and follow CnH2. To name an organic compound, follow these steps. First, count the carbons in the molecule. Next, identify the functional group and use a prefix or suffix accordingly. When adding a suffix that starts with a vowel, drop the final E from the parent chain name. For unsaturated compounds, replace ane with ene for double bonds or ine for triple bonds. Common compound classes have specific naming rules. Haloalkanes use prefixes like chloro or bromo. Alcohols use the suffix -ol. Aldehydes use -al. Ketones use -one, and carboxylic acids use -oic acid. Alkenes use -en, and alkynes use -ine. Carbon compounds have four main types of chemical reactions. The first is combustion, an oxidation reaction with oxygen, releasing heat and light. This produces carbon dioxide and water. The second type is oxidation, which involves adding oxygen to a substance. Alkaline potassium permanganate and acidified potassium dichromate are common oxidizing agents. The third type is addition reactions, where unsaturated hydrocarbons add hydrogen to form saturated hydrocarbons. The fourth type is substitution reactions, where one atom or group replaces another in a molecule. Examples include methane reacting with chlorine to form chloromethane and hydrogen chloride. Ethanol is a liquid at room temperature. It boils at 351 Kelvin and melts at 156 Kelvin. Ethanol mixes with water and is used in drinks, solvents, and biofuels. It reacts with sodium metal to produce sodium ethoxide and hydrogen gas. Ethanol can be lethal in small doses and causes health problems with long-term use. Denatured alcohol is ethanol made poisonous with methanol and dyes. Ethanolic acid or acetic acid is a weak acid used as a preservative in vinegar. It reacts with ethanol to form esters, which are used in perfumes and flavorings. Esters can also react with sodium hydroxide to produce soap through a process called saponification. Soaps are made of sodium or potassium salts of long-chain carboxylic acids. Each soap molecule has two ends: a hydrophilic end that interacts with water and a hydrophobic end that interacts with oil and fat. When soap is added to water with dirt or oil, it forms structures called micelles. These micelles surround oil and dirt droplets, allowing them to be rinsed away with water. Soap solutions appear cloudy due to micelles scattering light. Hard water can reduce soap's effectiveness, forming scum with calcium and magnesium ions. Detergents, on the other hand, work well in hard water, making them suitable for shampoos and laundry products. A covalent bond is formed when atoms share electron pairs. Some elements, like carbon, can bond with identical atoms to create chains. Carbon has 4 electrons available for bonding, making it versatile. Allotropes are different physical forms of elements with varying atomic arrangements. In organic chemistry, saturated compounds have single bonds between carbon atoms, while unsaturated compounds have double or triple bonds. Structural isomers have the same molecular formula, but different structures. A functional group determines a compound's chemical properties. An oxidizing agent adds oxygen to another substance, while a catalyst changes reaction rates without being consumed. Carbon has 2 key properties: tetravalency, with 4 electrons for bonding, and catenation, where atoms link in long chains. This allows carbon to form millions of compounds. Carbon atoms share electrons when bonding, creating stable structures. The arrangement of carbon atoms affects the compound's behavior. Carbon compounds can form straight chains, branched structures, or rings. Functional groups determine how a compound reacts, regardless of chain length. Homologous series are compounds with the same functional group but different numbers of carbon atoms. Carbon compounds undergo various reactions, including combustion, oxidation, addition, and substitution. Ethanol and ethanoic acid are 2 important compounds. Ethanol has industrial and domestic uses, while ethanoic acid is found in vinegar. Soap works by forming micelles when mixed with water. These clusters have oil-trapping ends inward and water-attracting ends outward, allowing grease and dirt to be washed away.